Yes, so I'm very much interested in understanding how molecules change their shape after they've been excited by light. And basically we would like to find out the different pathways within which they form their reaction products. And this is particularly relevant to important photochemical processes that happen in biological systems, as well as in industrial applications and so on and so forth. And one of the key classes of molecules is molecular photoswitches. So molecular photoswitches, you can think of it as switching on a light on and off. We provide the energy by pressing the button. In our case, we look at a molecular photoswitch by exciting the molecule with light, and the excitation causes the molecule to effectively switch from a on to off state and vice versa. Yes, so the SQS system at European XFEL is, I would say, one of the unique instruments in the world, because it combines something called reaction microscopy. This is when we basically generate fragments and ions from the molecular photoswitch that we're interested in investigating. What we would like to do is basically generate many charges into the molecule after we've basically illuminated it with X-rays. So this allows us to effectively have many charges in the molecule, and the charges can repel each other, and the fragments that are formed basically fly in opposing directions from which the charge is repelling against another charge partner. And this allows you to have an idea of basically the position or the starting position of the atoms and fragments in the molecule. So one can then reconstruct the three-dimensional and two-dimensional structure of molecules. And so to be able to do this, you need to combine both a high photon flux X-ray source, which exists at the European XFEL, together with the relevant instrumentation to actually measure the distribution of fragments and ions that are generated, that then we can effectively reconstruct the molecular structure. And we call this technique Coulomb explosion imaging, and we can actually then perform something called a molecular movie. So we're effectively molecular movie directors, and we can basically generate snapshots of the reaction that is undergoing. And one can do so by exciting a molecule with a specific wavelength of light, and the reaction is then begun. Effectively a clock watch, you can think of, has been started, and then we can take snapshots of the evolving structure with our X-ray, and then we can measure the ensuing structure information from the fragment emission directions and things like this. Molecular photoswitches play a very crucial role in, for example, how we see. So we have molecules in our eye. At the backbone of these molecules are carbon double bonds. So any kind of double bond in chemistry can have something called geometric isomerism. This is when you can go from a trans to a cis state. So what I mentioned earlier was about a switch that we press, and we can go from an on and off state. And one of the easiest ways to study this is to look at analogous molecules that have a similar, let's say, geometric isomerism, and one of these is called azobenzene. So azobenzene is where you have two phenyl rings, and in between these two phenyl rings you have a N-double-N bond. So this allows us to then really characterize exactly the reaction pathways that the molecule can undergo. So for example, many theoreticians and experimentalists over the last decades have predicted that if you start from a trans state, so the kind of an off switch, you can then go through many different pathways. You can, let's say, twist the ring and then rotate. You can invert and rotate. You can basically rotate and invert. And all of these different reaction pathways have differing outcomes. So basically we, in terms of society, have we may have potential issues with our eyesight, for example. So one of the future treatments could be basically tailoring specific excitation of our eye, for example, to trigger specific chemical reactions. And these could, for example, aid recovery of our eye in terms of the molecules that exist within the retina at the back of our eye. And so at the moment, no one has a clear understanding of exactly how the reaction mechanism of this important photochemical reaction occurs. So what we would like to provide ultimately are details of the transient in-between steps. And this is where the ability to make molecular movies of this evolving reaction becomes quite crucial.